Today we will start on AC circuits. AC circuits meaning the current is actually going left and right. Okay, so left and right. We are especially interested in sinusoidal varying currents. Okay, so that means the currents will go left and right, or not only unsteady, right? AC circuits usually mean, right, the current needs to go in opposite direction rather than it is unsteady. Okay, so this AC circuits that we are studying later, we will attach a source to this. But at the moment, there's no source. Source meaning electrical source, right? Okay. Now we have only two components in this circuit. You realize, right? This is called an LC circuit, right? Without a source, without an electrical source. So the energy will be oscillated among the electric field and the magnetic field. Okay. So how does it store charges? How does it store energy? Now you know from the previous cases, right, energy can be stored in terms of electric field, half E naught E squared, right? It can be stored in terms of magnetic field, half what's the formula? Half mu naught V squared, something like that, right? Okay. So, right, let's say there is no resistance to this circuit. That means no electrical resistance. There will be no energy dissipation. Well, then the energy will be oscillated between the electric field, converted, the electrostatic energy will be converted to magnetic field energy, right? Then it will be converted back to electric field energy. So let's maybe start off from one point here. Let's say this part, right? So when the current is zero, right, this is a fully charged capacitor, and the electric field is storing the energy, right? And since there's no current, right, the energy stored in the inductor, right, is zero because inductor's energy depends on half Li squared, right? So remember this half Li squared, right? This is the energy stored in the inductor. So this curly thing here, if you want to recap, right, curly thing here is an inductor, and this two parallel thing here is a capacitor, right? So a capacitor stores charges, inductor stores magnetic energy, right? Magnetic potential energy. Okay. So this part here will be entirely electrical energy stored. Right. Yeah. Now, let's go along this direction, right? Now, certainly the current will discharge through the inductor because it is a closed circuit, right? So the current will start to flow, right, in a clockwise manner, right? So when current starts to flow, half Li squared will not be zero, so there starts to be a magnetic field generated over here. So there will be a magnetic field energy, right? The bars represent the energy, so like you play a game like that, right? The bars represent the energy level, right? Then after that, maybe 1/8 of a cycle later, right? This is what happens, right? The entire capacitor discharges and the current is a maximum, right? So when there's maximum current, the energy stored in the inductor depends on half Li squared. So I is a maximum, therefore this energy stored in the inductor is a maximum. Okay? So the current is still going up until this point, and after that the current will start to decrease, but it's still in the same direction. Okay? So after that decreases and you have a split in energy, right? Because some of the charges have already flowed to this side of the capacitor, so it will start to accumulate positive charge again, right? So the polarity changes. You can see these two polarity, right? One is positive up, one is positive down. So then half a cycle later, this is what happens. So the polarity changes. So the current also varies sinusoidally, because if you see the half the cycle later, right, the current actually changes direction, right? So this is called an LC oscillation, right? Without energy dissipation, we are assuming that the wires do not have any electrical resistance. Okay. In this colorful picture, it's easier to read, right? But unfortunately, the notes are not colored, quite tough. Right, let's look at the energy. Now, if there's no energy dissipation, that means this total energy will be a constant. So the total energy represented by U will be the magnetic energy stored and the electric field energy stored. So together, add up these two, you will get half Li squared plus Q squared over 2C. But this is actually the energy stored in the capacitor and inductor and capacitor respectively. I think there's a C, this C prime. It's just C. I think I added a C prime. It's just C, okay? Let's cancel this. Yeah. Right. Now, if you differentiate du dt with respect to time, because u is a constant, so if you differentiate a constant with respect to time, you get 0, right? So let's differentiate this one. Now, differentiate with respect to time. L is a constant, take it out of differentiation. Then you differentiate I, but I is a I squared term, right? So if you differentiate I, you should get 2I and di dt, right? 2I di dt. But, okay. 2I di dt. So the 2I di dt will cancel away the 2 in the denominator here. Right. So the 2 disappears. So you get only Li di dt, right? And Q squared over 2C. Q squared, Q is again a function of time because the charge on the capacitor will decrease and increase, right? So it's again a function of time. So you differentiate Q squared, you will get 2Q dQ dt, right? But the 2 will again cancel away with the denominator 2 here. Therefore, you will get Q over C dQ over dt, right? C is a constant, so you take it out of the differentiation. Okay. Now, then you substitute this di dt to be equal to d squared q dt squared. Because I is dq dt, so if you differentiate di again, then you will get d squared q d squared dt squared. Right? Okay? Because I is dq dt. Right. So differentiate I one more time. This will give you d squared q dt squared. Okay? Second order. Or d dt dq dt first. Okay? Right? Then you substitute this di dt from here, right? Substitute with d squared q dt squared. So overall, you have a function, right, that is only dependent on q, second order differentiation, right? Okay. You know what happens to this dq dt? This is I, right? So there's an I over here. So the right hand side is 0 because of the fact that there is no change in the total energy, right? So du dt will be 0. So dq dt being I, right? So this term here will be qi over c. But I is a common factor for these two terms. So you cancel away the I. Oh. So you're left with an equation that's a second order. Okay? This second order differentiation equation you will learn more in the chapter called oscillation, right? Okay. Then if you solve this second order differentiation, the solution will be a sinusoidal solution, a form sinusoidal solution. This is also in your H2 syllabus. Okay, Q, right, will be big Q cos omega t or sine omega t plus phi, right? So it's either cosine or sine, either way, no preference, right? Phi is just an angle that depends on the initial situation where you start off, right? Whether you start off at this stage or certain stage, right? So, right, it's arbitrary, okay? And this Q here, if I write it big Q, means it's the maximum value of the charge stored in the capacitor, right? Whereas I will be the maximum value for the current. Okay? So when you solve for Q, right, you get this equation. Then again, you put back to this Q dt again. Then you will get I as a function of the I will be also sinusoidal with time. Because once you get the cosine function, you differentiate, it's also sinusoidal, right? So you differentiate cosine, you get minus sine, okay? Right. Then omega will be 1 over root LC, right? If you try and compare the terms, right? Try and compare the terms, you get omega is equals to 1 over root LC. Okay? You can try it yourself. Yeah. It's a practice. Okay, try to see that omega is 1 over LC. Now, this omega has a special meaning. It's called the angular frequency. Right? Angular frequency, which is related to 2 pi f. Right? So it's equal to 1 over root of c. Okay. Now, the previous part is without. Right? They will ask you circuits without electrical source. But sometimes, right, they put in an AC generator with a source. So it's always an AC source, right, because we are focusing on AC currents. Okay, so you connect an AC source, like for this case, we connect just to a pure load. A pure load is also called a resistive load. Okay, this resistance wire is without any inductance, without any capacitor effects. Okay, pure resistance, right? So we are interested in the voltage across it and the current in the circuit, right? Since it's AC and you will see this sinusoidal waveform, you can be quite safe, right? Or rather, it's correct to assume that the voltage is actually sinusoidally varying with time. So the potential difference across R will be En sine omega dt. Omega d, the d represents, I think, driver, the driving circuit, right? So Em, this one will represent the maximum value for the EMF of the source. Okay? So that will be equals to VR sine omega t. So Em is equal to VR. VR is the maximum value, the PD of course, right? Because by Kirchhoff's second rule, right, the maximum value for Em must be equal to VR. Okay. Now, if you want to find the current through the resistor, you just take VR divided by the resistance. You will get VR over R sine omega dt, sine omega t. Right, that's because of using the fact that it's I is actually equals to the V over R. Right? This one's simple, right? Okay. So, yeah. Now, if you compare this equation with the more general one, which is IR sine omega t minus phi, right? Because sometimes we will try to assume this formula first. Later, I'll tell you why. Right? Sine omega t minus phi. Sometimes the phi may not be 0, but in this case, if it's a pure resistor, right, the voltage and the current is actually in step with each other, exactly matches. So phi will be 0, right? And the maximum value for VR will be IR times R. Right? So VR and IR. Now, it's very useful to represent it by some phasors, okay, phasors. Because if you draw phasors, then one look you will know what's happening, and it's very easy to find the relationship between the phase angle between the current and the voltage. So phasors is actually quite useful in our case. And also phasors, actually they are just arrows, right? But with a constant magnitude, rotating about the y-axis, the usual axis, right? So phasor diagram is actually very useful in electrical circuits, right? So now phasors have the following properties: angular speed, right? Angular speed, just now we went through something like that. It's actually the term omega, right? So the angular speed is actually usually anti-clock. No? It rotates. The phasor always rotates anti-clockwise or counterclockwise, right? And the speed of rotation is omega, right? Okay. And if you look at the VR and IR equation, the speed of rotation for the VR phasor and the IR phasor, which is represented by arrows, is actually the same because they are the same omega. Okay? And the length of each phasor, quite conveniently, will represent the amplitude, the maximum value. It doesn't change. It doesn't change with time, right? So the length of each phasor doesn't change with time. But it will of course change. I mean, the current, right, at a certain time will of course change. What I'm saying that doesn't change is actually this one. This one doesn't change. But however, small I will change because it's a function of time. Oh. Okay. So how do you see during a phasor diagram is when the vector IR is actually a component of a sine component. Yeah, a sine component. So it's actually usually, let me see, it's being projected onto the y-axis. Yeah. So it's the length on the y-axis that represents this one. And the length on the y-axis represents the magnitude of IR, small IR, and this one will change. Okay? Whereas the length of the phasor doesn't change. Right, later we'll go through the things. Yeah, okay, the projection. Right. Okay, look at this resistive load with AC source. Right. Naturally, phi will be 0. So, as you can see, these two will be the phasor of V and I respectively, right? They will be always in phase. That means always in step. Because phi is 0. Right? And the length doesn't change for, let's say, V. Right? It doesn't change. And I also, the length of IR doesn't change. But the component here will change. Because this component here will be dependent on the angle, right? Omega t. Then the angle will be dependent on time. So this one will change. So this length will change. This length will change represent the magnitude of I will change. Right? So, I mean, if you draw a phasor diagram, it's easier to see. Right? If you don't like a phasor diagram, then you can do this. Okay? You can see that the V will change. Right? The small I will change. Right? Okay? But since phasor diagram is inside the syllabus, we'll just include it in. Capacitive load. Okay, let's connect a generator to a pure capacitive load, like this. So again, by Kirchhoff's second law, VC will be equals to VC. The VC will be equals to the voltage across the capacitor. Right? Okay. So VC sine omega t, right? So, but QC, that is the charge stored in the capacitor. That one you have to remember the formula. Q is equal to C times V, right? You still remember? Q, the charge stored in the capacitor is C times V. That one from last term, C times V. Right? But if you want a maximum charge stored, right, this will be the maximum charge stored. That will be C times the maximum value for the voltage across the capacitor. So C times the maximum value for VC. Right? Now, again, how do you get I? Just perform a differentiation. I is equals to dq dt, this one. Right? Then you will get the expression, this one. Okay. Now, we define something called XC. This XC is called a capacitive reactance. Just know the name, capacitive reactance. Right? Capacitive reactance is related to 1 over omega C. Right? I think, why do you want to do this? Because I think this will make the units the same later on when you see. The units will be probably in ohms. I think so. Right? Okay? You can guess, right? You see, XC, VC over XC give you current. Psi is unitless, that means this will force this to be the units of resistance. So it's something like a resistance. Oh, so there's a purpose for defining this. So capacitive reactance of a capacitor, XC. Right? It does have a unit there, SI unit of omega. Sorry, I cannot remember. So that's why I sometimes infer, right? Because we don't teach this one by profession, but I mean, once in a while, this time around, then they put us in. Right? So, yeah. So VC equals to IC XC, right? So IC is VC or XC sine omega t plus 90. Where do you get the 90? Okay. Probably this one you have to refer to, let me see if there's a diagram later on. Now, where do you get the 90? Okay, if you compare this equation, IC, this one, right, with a 90 degree, and this equation, omega CVC cosine omega t. Right? Of course, this equation has to be the same. But to make it the same, right, let's say I want to convert this one to a sine function. Then you go and do some trigo, right? You will find that it has to be sine omega t plus 90. Oh, because sine of an angle is equals to cosine 90 minus, or rather sine theta is equal to cosine 90 minus theta. Right? So you want to make it sine. Reason, because you want to compare the sine function, right, with the voltage. Right? So sine and sine, right, is easier to compare. So you can compare the phase angle of IC and the phase angle of BC. See how they compare. So we can write IC is equal to big IC sine omega t minus phi. So you compare, right, you will get phi equals to minus 90. That means you get minus means lagging. The current actually is rotating behind the voltage phasor. Right. Lagging. Okay. This is sine. Sine. Leads by 90. Why say leads here? Comparing, we have phi equals to minus 90. Correct. So IC leads by 90. Okay, VC is this one, right? So this one is the normal one, like we have for just now, right? Oh, okay, I know why. Because our general result is you have IC is equals to sine omega t. No need. Just compare this one. Sine omega t plus 90. When you see plus all here, plus 90, right? Means no need to do anything, it's just plus 90. That means it's leading, or it's actually having a bigger fixed angle. So it leads. Okay? So lead by how much? Lead by 90. So for this angle, we just add another 90. So correct, it's leading. So it's IC. So we will face phasor diagram, but it's quite easy to see. You see? IC and VC. Actually, so this is the relationship between the current and VC. So you can try to imagine that VC and IC, they are out of phase by 90 degrees, with IC leading it. Oh. Okay? Right. But the resistance one is easy to remember. That one's easy to visualize. That one. VC and VR and IR, that one's easier. Because we've always been doing that. But the VC and IC is hard to imagine. Right? But with a phasor diagram that will help. Okay. Right. So the current will lead. Right? That means it will rotate to a bigger angle at an earlier time. Right? This is called leading. Okay? Leading and lagging, we will come to this again in the chapter waves. Okay? In the chapter called waves. Right? I will take this one, waves, in the H2 lecture. Okay? So not too bad. So we'll redo this one again. Okay. Now let's come to the inductive loop. Inductive loop. So you connect the source again, the AC source to an inductor, right? And again you will see that the current and the voltage is actually out of phase by some angle. We want to find this angle, right? So VL sine omega t, and VL of course will be L di dt. This is from definition again, right? Because the voltage across the inductor is L di dt. So by Kirchhoff's second law, right, loop rule, then the VL must be definitely L di dt. Okay, so di dt, that will give you VL over L sine omega t just by differentiation of where is this thing called? V over L sine omega t. V over L. Oh yeah, I mean quite easy, right? It's from these two equations, right? So we get di dt equal to V L over L sine omega t, right? Now we try to perform an integration the other way, opposite to a differentiation. So we integrate, IL will be integration of DIL. So it becomes VL over L, right? And sine omega t dt, di. You know how to do this? Now, di, right, you can get by bringing dt over. So you get V over L sine omega t dt. Okay? So you perform integration, you will get the function of I. Right? Okay? And when you perform a integration, then it will be opposite to a differentiation, then you must imagine. Right? When you do an integration, sine will become minus cosine. So that's why it's a negative sign. Right? But you need to divide by omega, because this is a composite function. Right? So you need to divide by omega. So try and learn some integration yourself. Okay, basic one. But I think on the actual day of the test, you won't involve integration. Differentiation maybe a little bit, but I don't think integration is required. Just because, but we have to learn it because it's quite fundamental. Right. Then we define XL again for the new term, This is called the inductive reactance. Of course, the units, you guess, it will be ohms, right? This reactance will be omega L. Oh, right. And from comparison, we find that I is actually VL over XL sine omega t minus 90. If you get minus, that means this will cause the current is actually giving you a smaller angle. If it gives you a smaller angle, that means it's lagging, right, the voltage. So it lags the voltage by 90 degrees. So if it lags the voltage by 90 degrees, then you can see your phasor diagram is actually quite clear. It's actually counterclockwise. Because the phasor will rotate counterclockwise by definition. Okay? So if it's lagging, then it will be clockwise. The angle will be smaller. How much smaller? Omega t minus 90. Okay? If you don't like phasor diagram, then you can draw something like that, but it's very difficult to see sometimes where the 90 corresponds to. Okay? Okay, we have the individual components. Now we will analyze the whole thing. Put the RLC in series. Okay, there will be RLC in parallel, but it doesn't seem to be in series. So we will only concentrate on RLC circuit series. Right. RLC parallel. No RLC parallel. RLC series is usually series. Okay. RLC cannot. Not, I think it's not useful. RLC in parallel. RLC series, it will be useful in like radio circuits, right? It will be useful. Sign our attendance. Okay. So if you connect the electrical source, right, to a RLC circuit, then you have three components together, right? Of course, it will become messy if you don't have a phasor diagram to help. Okay. Right. Let's look at the source first. Okay. The source will have the sinusoidal function because it's an AC. So Em sine omega t, right, is applied EMF, right? So the current, we actually don't know whether the current leads or lags the EMF or whether it is leading or lagging. So we just assign a general minus pi, right? Generally, the general equation will be minus pi. Okay, so we just assign a general minus pi over here. Okay. So if you follow the phasor diagram, right, you first draw the current. The current will be like the length over here will represent the amplitude of the current, right? The angle represented here, right, will be the angle this one, omega t minus pi, right? So the projection on the y-axis will actually give you the instantaneous value for the current. Okay, so this phasor will again rotate anti-clockwise. Okay, now first thing to note that the voltage and the current for resistors, they will always be in phase. Oh, this is one thing to note. That one is quite simple, right? It's always in phase. Just now we have also come to the individual circuit, right? We see that the voltage and the current for the resistor, pure resistor, they are always in phase. Then for VL, the inductor, the voltage of the inductor will lead the current. Correct? Let's see. Back here. Okay. This is the inductor, right? So, it's the inductor. Yeah, this is the inductor. So the voltage actually is leading the current by 90 degrees. Oh. But now this phasor diagram, the below one, this is not VL, right? This is VL. So remember, VL leads IL. So now we are drawing the IL at the angle of the VL. So you look here again. Okay, we are drawing this as, imagine this as the I. IL. Okay, then what is happening is that the VL will lead the I. Okay, I, R and V, R is always of the same phase, right? So the current is always in phase with VR, right? So VL will lead the current, which is in phase with VR. So this is just treat it as the current. Okay, the current will always follow the VR. So if you draw the phasor diagram, VL will lead VR. And similarly, VC will lag VR by 90. Okay? This is how the phasor diagram will look like. Then you combine everything, add them up vectorially, just like what you did, right? Okay, so is this what you did? Yeah. So you look at VL and VC, they are opposite, right? So let's say VL is longer, so VL minus VC will have a resultant this way. VR this way. So the two resultant VR, the resultant of these two VR and VL minus VC will be at this angle, the red colored, right? EM. Right. So this is the value for the voltage across, right? Because the voltages add up must be equal to the voltage of the EMF, right? But they don't add up algebraically, right? This is how they add up, because the current is not really in phase, so the voltage will not be really in phase also. So they have to add up vectorially. So this shows how useful is the vector diagram, right? So the EMF will not be exactly being added up algebraically, right? Okay. Now, if you have E across, you get E is equal to VR, VC plus VL, right? Yeah, but this is not algebra addition, right? It's just because there's a function to it, right? VR is actually a function, sine function or whatever. Okay? Now, EM squared. Oh yeah, this one is always true, correct? VR plus VC plus VL, this is always true. This is algebraic, correct? Correct. This is algebraic. But this one, right? This one is not. Okay, the amplitude is not algebraic. Yeah. The amplitude will be EM squared equals to VR squared plus VL plus VC squared because of this vector. Right? So this refers to the amplitude. But the algebraic one, that is true because of the Kirchhoff second law. Right? So they will add up algebraically. But the amplitudes won't. Right? VL minus VC, right? This one is in full caps. Right? This is the maximum value. They won't add up algebraically. Right? Okay? So EM squared, EM will not be equal to VR plus VL plus VC. Right? Instead, this is the relationship. Okay, according to this diagram, phasor diagram. Okay? Then we can substitute with the resistance and the following reactive capacitance and the reactive inductance. Right? Because these are of the units of ohms. Right? So you can be sure that these are all of the units of voltage squared. Okay? And if you try to calculate the current, the maximum current, because this one is a caps, in caps, so this is the maximum current, that will be EM over root R squared plus XL minus XC squared. This whole thing here can be just imagined to be some sort of resistance. So there's some sort of resistance, usually we don't call it the resistance, we call it the impedance, right? Z. Okay? Because XL and XC is not really resistance, right? So it's some sort of resistance. So we call it a new word, impedance. from here, we can get some useful relationship. Tangent phi, this one, right, from this diagram will be this, and you can solve for phi, right? That is the phase angle between the EM vector, that means the voltage of the source, the voltage of the source vector, right? Because it's the rate phasor, right? And between the VR. Okay, VR is also the same angle with I, the current, remember. Okay, so it's very useful to solve for the phi. Right. Now, so we have some cases, XL more than XC. Right. XC more than XL. Now, this one you have to just refer back to the phasor diagram. So if XL is more than XC, so this, referring back to the phasor diagram, this one, right? If XL is more than XC, that means you will get this case, right? Because this XL will be longer than VC. So you will get this case. Right? XL more than XC. Yeah. But why do you get this? This one refers to, you notice you have shifted the EM. In the previous diagram, the EM was a certain direction. Now you have shifted the EM to the reference, right? Some angle above the x-axis. Right? So I will be following VR, right? So EM will be leading. Oh. If you compare back to this diagram, right? EM is here, VR is here. So now I draw EM like this. So VR will be here, or I will be here. Okay? So this is what it means. So the current will be in that particular direction. Right? Remember, current and VR, they are in phase. Okay, VR, they are in phase. Okay. So positive phi means that the current lags the EMF, right? The phasor is vertical later and the curve peaks later, so it's lagging, right? This anything means it's just for you to remember. Any means don't know what now. Some don't know. It's nothing physical. No physical meaning to that. So don't remember. I also can't remember. So that means it's for you to remember something. But I cannot even remember any. What does it mean? So don't remember. No need. Right. Okay. Just remember XL more than XC, what happens, right? And XL less than XC, what happens? This is also another thing I see. It's help you remember. But the thing is that I cannot remember what's ICE. So it cannot help me remember. Okay, too many things. So negative phi. So now you refer back to that diagram. Okay, you imagine, because I don't have the diagram, so you imagine that VC now is bigger than VL. So the phasor of this one will point this way. Yeah, will point this way. Okay. So if you draw EM, then what is it like that? I, EM, XC, correct. Okay. This phasor will be here, right? So I will now lead the voltage phasor, right? So I leads voltage phasor. I leads voltage phasor. Ah, correct. Okay, because you let the voltage phasor to be the reference again. So we shift back from the EM, right? So I leads, so it is counterclockwise first, right? So when it's leading, right, you want to draw a representation, you be like that, right? Okay. Now, XL equals to XC. That's very interesting because you will see that this will correspond to the value where the instance when the impedance is actually the smallest. Because if you look at this thing, right, R squared plus XL minus XC squared. Because of the square term, XL minus XC will always, whether it's negative or positive, is not important. Because if you square it, it becomes a positive value. So the minimum value that you can have for Z is when XL equal to XC, where your impedance is just only equals to R. Oh, that's the smallest impedance. Okay, so when the smallest impedance, your current will be largest. So that's when you will need to apply this most of the cases, right? So yeah, XL equal to XC. Right. Then you can see that if XL equal to XC, then the two components VL and VC will cancel out because they are the same value. Okay? So I and EM will be exactly in phase, right? Because I will just follow R only. Right? Okay? So this is the term given whereby the current is largest, right? Because the impedance being the smallest. So for a given value for R, then you have resonance. Resonance is the term given that for a certain condition, right, you have maximum value or the maximum current amplitudes, right? Yeah. Okay. You will learn resonance in oscillations, the part of oscillations, right, where you have large amplitude oscillations. Okay, but electrically you also can have resonance. Okay, this is when XL equal to XC. So if you put your how do you get XL equal to XC? Right, you just equate to the normal omega L and the normal 1 over omega C. This is how you define your XL initially and your XC initially. Right, then if you apply the driver source, right, give it a frequency of 1 over root L of C, right, then that will correspond to the natural frequency RLC. Okay, so if the source, right, the source is up to us to choose to give it a frequency. But if you give it a frequency that happens to be having a value of 1 over root LC, this will cause the circuit to resonate. That means the current in the circuit will be largest. Okay? Because the natural frequency being that of the circuit, which is 1 over root LC. Okay? Now let's look at power in the AC circuits. Basically, there is no power dissipation in the magnetic field and the electric field, right? The average energy stored in the electric field basically is the same, right? The only energy that is being dissipated is actually the resistor being transformed to heat. Okay, so P is equal to I squared R, but we have to put the I value inside, so it becomes I sine omega t minus phi, right? Squared R. Okay, so you get I squared R sine omega t minus pi. Now, irregardless of whatever, right, over one complete cycle of sine squared, the value is half. So overall, the power dissipated will be half. Okay, where is it? Yeah, here. Half I squared R. Okay. Now, what do you mean by this? Sine square theta means this one, right? This term, there's a sine square theta term here. Right? But we want to find the average power, right, over one cycle, because actually over one cycle is enough, because it will repeat itself again, right? Now, how do you show that this value sine square theta is half? You have to perform an integration You can try this at home. Do sine square theta divided by 2 pi. Because you are differentiating theta over 1 cycle, so you have to put d theta here, and then 0 to pi. Okay. So you see whether you can half. Okay, try. Of course, to integrate sine square, you can use the double angle formula to substitute. Okay, just try. Okay, right. So yeah, this is for resonance. You can have resonance graph comparing the resonance for omega d over omega. You can see that when omega d over omega, the natural frequency is equal, right? You get 1. Right? At 1, you will get the largest value for the current amplitude. But it also depends on resistance, right? Okay. Now, so the average power, right, that will be I squared R over 2 from here. I squared R over 2, because the sine square term, right, will be half. So I squared R over 2. Okay. The sine square curve will look like this. But you realize actually this one is also sinusoidal, right? Sinusoidal. It's just sinusoidally but shifted. You can use the double angular formula. You can see it's also sinusoidal, right? It just shifted up and down. Then sinusoidal also, right? You put the axis as this dotted line, right? You can see it's sinusoidal. Okay. Now, sometimes we will have, when we do AC circuits, especially the sinusoidal ones, right? We have a root mean square value. This root mean square value is, how do you define? Root mean square means you perform the function of the other way. Because in mathematics, right, root mean square means you always perform square, mean, and root. This one you learn next year in your year 2, root mean square value. So you perform square, mean, root. So in order, let's say if you want to find the root mean square value for a sinusoidal function for I, right, then I will be I naught sine omega t, right? So to find the root mean square function, that means we follow square mean root. So we square this function first, squaring. Okay. Then after that, we take the mean. Take the mean means we take the average. Take the average. But take the average of what? Take the average over what? You have to take the average over 1 cycle. Because after 1 cycle, it will repeat itself. It's a sinusoidal function. Okay? So, you have to do this. Right? If you take average, you always try to integrate. So, I naught sine squared omega t dt divided by t. Right? Taking the average. When you put the integrals as 0 and t. Finally, it comes to r. R means taking the square root. So the whole function, take the square root. Okay? You go and try this at home, then you will probably get I naught over root 2 for sinusoidal function. Again, you got to use the double angle formula, right? Because you can't integrate sine squared directly. Okay? So the I root mean square will be replaced by I naught over root 2. So there's I naught over root 2 here. So you can I root mean square R. So the P average, right, will be always I root mean square R. Okay? So same as B root mean square and so on. Right? Okay? Where in this case your V is the maximum voltage, right? EM is the maximum value for the maximum value for the voltage source, right? So if you were to write the I root mean square in terms of E root mean square over Z, right? If this is non-resonance case, right, you have this E root mean square over Z, right? E root mean square over Z, right? So just put the Z value, which is the impedance, right? You will get, then we can also write P average is equals to P equals to E root mean square, I root mean square, R over Z. So there's a factor R over Z. I think this one is called the power factor, R over Z, right? Okay? R over Z. So if Z is equal to R, then the power factor will be 1. Okay? Right. So otherwise, right, that is the general formula. P average will be E root mean square, I root mean square, R over Z. Right? Okay. But R over Z is also equals from the phasor diagram. Right? Page 11, figure D. I think from the phasor diagram. Is it the phasor diagram? Page 11, figure D. Yeah, it's the phasor diagram. Oh, right? You get cosine phi equal to VR over dm. So you will get that to be R over Z. Right? So P average will be E root mean square, I root mean square cosine phi. Right? This cosine phi, which is your R over Z, is called the power factor. So to maximize this rate of energy that's being dissipated in the resistive load, you have to put the power factor as close to 1 as possible. Right? Okay? Okay, that's it for this, but we have to try and do some tutorial. Oh. Because if not, we are running out of time for waves. I think waves and superposition will be quite an important topic. Right? Okay? This one I asked them whether previously there is, but I think not too much. Okay, never mind. Let's do the tutorial. Okay, figure A shows a rod of resistive material. The resistance per unit length of the rod increases in the positive direction of the x-axis. So actually, the per unit length resistance is not constant, so it increases. At any position x along the rod, right? You have this 0 to 1 meter dx to this figure A. The resistance dr of a differential section of dx is given by pi x dx. I think this one is just and practice of integration, right? So dr is pi x dx. That's a section where dr is in ohms and x in meters. B. What's the question? Figure A shows. Okay, figure B shows a narrow section, not B. I thought it's a question. I can't see the question. Okay, it just means figure B. Figure B shows a narrow section, right? Such a narrow section. You have to slice off a length of the rod between 0 and some position x equal to L, which you don't know, right? So probably it's between 0 to 1 meter, right? And then connect the length to a battery with PD 5 volt in C. Okay. You want the current in the length to transfer energy to the thermal energy at the rate of 200 watts. That means you want the power dissipated in the resistor to be 200 watts. At what position x equal to L should you cut? Okay. So answer should be somewhere between 0 to 1 meter. Okay. Okay, let's go down all the way. Now, you can use your previous knowledge, right? Because we started off with Ohm's law and everything, right? P equal to V squared over R, where the V represents the P is 200 watts across the section of the resistor. Okay? Right, and 5 volts is of course the PD across the resistor. The PD across the resistor must be matches the PD across the battery, right? Because now imagine you cut away some parts, right, and then you connect to the battery, right? The PD across that resistor must be 5 volts also. So V squared over R, but R you have to perform a integration, right, to find the total resistance. The resistance is not constant per unit length, so it actually varies with X. The bigger the X value, the bigger is the resistance per unit length. So you must use pi x dx. Okay? So you solve for L, you get 0.224 meter. So it's within 1 meter, so correct. So that's a double check. Okay? You need not copy, I'll send everything to you. Okay? Just you want, just copy the answer, then you're going to try. Okay? Now let's go to question 2. Oh, looks complicated. In the figure below, 20 volt battery is connected across capacitors of capacitance C1, C6. Where's C1? I can't see. Oh, no, here. C1. C1, C, all 3, 6 resistors. Okay, but they are different values. Right. What are the equivalent capacitance, CEQ, of the capacitors, and B, the charge stored by CEQ? What are V1, Q1, so on, a lot of things to ask. Okay, so you have to redraw when you see this type of circuits, you have to redraw. Okay. Now, one way, right? This one doesn't suit your orientation, you just flip. Right, just do that. Okay? Then you'll see that actually this part will be in series with the upper part. Right. Then the upper part, right, this one doesn't suit you. C2 actually will be parallel with C5, C3. Of course, C5 and C3, that's the fundamental unit, right? That is in series. Right. So C3, C5 in series, but it's actually in parallel with C4 and C2. Then after that, this whole thing actually will be in series with C6 and C1 in parallel. Okay. So you can try and draw. Oops, I never redraw. Okay, never mind. I redraw it here. Okay. C6, C1 will be in parallel, right? So this will join up like this. Right. It doesn't matter whether you put C1 here or here. Doesn't matter. It just tricks the eye only, right? Then after that, it will be in series with C4, C5, C3, and C2, right? Which is the other So C3, C5. Right. Again, the C2 is actually drawn over at side, but you can draw it over this part. Okay. So this is C2. And the C4 is here. This actually is the connecting part, right, which is this whole thing. Okay, it doesn't matter, electrically it looks like this, right? So this is the equivalent capacitance of the circuit. Now, you can try to work out this one, right? Fundamentally, you just work it out, right? Working this C3 and C5 in series, you work out the effective capacitance of this one first. Then you work out the effective capacitance of these three in parallel. Then after you work out the effective capacitance of these two in parallel. Then you work out the effective capacitance of this one as a whole in series with this one as a whole. That will be the total C equivalent. Okay, then let's look at the answer. Okay. So after working out, the charge dot will be just V times CEQ. V is the PD of the source, right? Then you get 60 microcoulomb. V1 10 volt. V1 is 10 volt. D this one looks very messy over here. You just go back and try. Maybe you copy down the answer, right? Go and try. Right? Oh. But the circuit looks like this, right? This one is the most important part. Okay? Then the rest will be just using Q equal to CV, right? Or you want to go through? Let's go through. Go through every part. Can think. Oh, interesting. This one is going through every part. It's just a practice. V1, Q1, Q2, V3. Just stop CEQ. Oh, they're asking V1, right? That means V1 is the PD across C1. That's all. Across, yeah, what are V1? V1 is the PD across C1, but you have V, right? This is V1 plus V2, right? That will give you V. But what can you say about these two? The charge stop will be the same for this part and this part, because these two are in series. So the charge stop for this part will be equal to the charge stop for this part, right? Because you're connecting this one to a voltage source like this. Okay. Now we are back to DC circuit. Because capacitors can't work for AC, because you will be charging and discharging at the same time. Okay? So you are connecting like this, right? So remember, if we have two capacitors in series, right? The charge stop here will be equal to the charge stop here. Same. Right? What is different is the voltage. Right? The voltage across this one is the different as the voltage across. Okay? Never mind, you go and practice lah. You can copy down the answer, just go and practice. Okay, treat it as a practice. I think I can look out some books on this one, right? Some practice, this one. Okay. You want to copy down the answers first? Huh? Huh? Yeah, I email you the solution. Okay. But not today, because probably you can't finish the tutorial. That means I'll email you maybe next week. Can? Because you also will not be in quite a good mood, right? To do it these few days, right? Because you'll be celebrating mood and also, yeah. Oh, yeah. Email you, don't worry. Okay. But just go and try first, if you don't have time. I mean, because it can be a help, because you will be studying for your you have studied for your mid-year. I know it's very busy for some of you, right? Okay. Now, let's look at this one. In the figure below, C1 is 10 microfarad, C2 20 microfarad, C3 25. This one looks much neater, but I don't know whether the question is difficult. If no capacitor can withstand a PD of more than 100 volt without failure, what are the magnitude of the maximum PD that can exist between points A and B? And B, the maximum energy that can be stored in the 3 capacitor arrangement, right? Then you must remember, right, half CV squared, right? You add all the energy, half CV squared, everything together, right? But the thing is that no capacitor can withstand a PD of 100 volts. That's the difficult part. Because, so they're asking about this. Okay, between point A and B, what is the maximum PD, right, that can be applied? But if you have 3 capacitors in series, then the Q will be always the same. Remember, the Q will always be the same for C1, C2, C3 connected in series. Okay? But we want to make sure that no capacitor will increase to 100 volt. So we can try, but we know that if this is V1 and this is V2 and this is V3, right? You add them up, it must be equals to the PD of the battery. Right? The PD of the battery is not given. So you do more than 100 volts. Or rather, the PD of V1 plus V2 plus V3, we don't know it, right? So we are supposed to find what is the magnitude of the maximum potential difference that can exist between A and B. But we must add these 3 together, right? So that the PD, right, none of them in here can exceed 100. It's not AB, right? Okay, let's look at the solution. Okay, the charge is the same on the 3 capacitors as drawn there, right? Because it's in series, you can only take this amount, and this one can only let go that amount, so on and so forth. So if it's in series, always remember the charge must be the same. Right? The maximum charge is obtained by using Q over C1 equals to 100. Why? Because they want C1, is it? Let's reread the question. I forgot. Oh, if no capacitor, that means none of the capacitor can withstand a PD of more than 100. Okay. So, no capacitor. So, none of them. So, we let it be the maximum value, right? So, Q over C1, that will give you V1. We just let it to be the maximum value 100. Oh. So, we work out, with the value for C1, we can work out Q. That is the maximum charge that can be stored by C1. Okay? Then you get Q. Right. So this Q also represents the Q for all the three because they're in series. Okay? Right. So the maximum PD between A and B, that will be equals to 1000 over C1. That will give you Q over C1, that will give you V1. So V1 plus V2 plus V3, that's what it's saying. Okay? V1 plus V2 plus V3, that will give you 190 by substituting the values for C1, C2, C3 inside. That's it. No? Understand? Okay? So you can try the values, right? Sub in the values to see whether that none of the capacitor actually exceeds 100 volts. Yeah. But why you use Q over C1 and not Q over C2? Why? Or Q over C3? Why you choose Q over C1? Huh? How do you know I need to choose Q over C1? C1 is largest, smallest. Yeah. C1 is smallest, correct. So if it's smallest, that means it's easier to reach 100 volts. Correct. So you have to choose the smallest one. Oh. Correct. Good idea. Right, C1 is the smallest. And you don't choose Q over C2 or C3. Okay, choose C1. Okay. Yeah, that's a crucial point. Correct. C1 is the smallest. Very good. Then part B. Right, the total energy stored will be Q squared over 2C1 plus Q squared over 2C2 plus Q squared over 2C3. That is from the formula. Right, then because of the value of Q and the values for C1, C2, C3, you can put it inside. Now, let's look at number 4. I won't go too late, don't worry. Because we are running out of time also. Okay, the step of copper thickness B is equals to 2 mm is thrust into a parallel plate capacitor of plate area 2.4 cm squared and plate separation D is equals to 5 mm as shown. So D is given here and B is the copper slab. This one quite interesting question, right? Because the slab can be replaced by something, the copper slab. The slab is exactly halfway between the plates. What is the capacitance after the slab is introduced? Right. If a charge Q is equal to 3.4, this one is later on. Right. Now, the copper slab can be reduced to something like that because copper is a perfect, or rather near, you can treat it as a conductor, right? So the copper can totally be replaced by this one. Alright. This one. Okay? So the copper just replaced by the capacitor, or rather two plates over here. Because first, perfect conductor, so you can rearrange the charge within the copper. Right, so you just equivalently, you can draw a two plate here. Right. So, and it turns out that if you draw like that, then it becomes two capacitors in series. Right? If it's two capacitors in series, then the equivalent will be C over 2. Right? Then C over 2. Right? C is just E naught. C over 2, C is just E naught A over D minus b over 2. That's one of them. You know why d minus b over 2? Because d minus b is actually this one and this one, the distance. So you have to divide by 2 again to get in the separation between the plate. Right. Where do you get this formula? It's from the previous. C is equal to E naught A over D. Right? Then just put in all the values, then you will get the answer. Okay. Stop here. Okay. Stop here. Then try the R. Okay. I think yeah. You look tired. Okay. So we will carry on this next week, and then probably I'll give you a new set of notes really for waves and superposition. Right.